Alright, hello guys. Today I will be solving this problem called case symbol in grammar. I actually did homework on this one actually. I had some inspiration about solutions. So probably wouldn't take a while until I come up with the basic idea to solve the problem. But of course, I'm such a bad programmer. Will be take a lot of time implementing the solution, so no worries. Um, so let's just dive right in. Let me make it bigger for you guys. Is it big enough? All right. Then, first things first, git check out problem. What's this problem called? Case symbol in grammar. Case symbol in grammar. Case symbol in grammar. All right. What? Git check. Okay. Hold on. So I need to create a new branch. And then make directory, copy this string, put it, move to the directory that I have just created. Let's open up a memo.com, no, memo.md. Step 1. Okay, so experiment. First things first. Let me read it aloud. The problem description. We build a table of n rows. We start by writing 0 in the first row. Now in every subsequent row, we look at the previous row and replace each occurrence of 0 with 0, 1, and each occurrence of 1 with 1, 0. For example, you have 3 rows. The first row is 0, the second row is 0, 1, and the third row is 0, 1, 1, 0. Given two integer n and k, return the kth symbol in the nth row of a table of n. So what's going to happen is that you have n. Alright, you have 0 first. Let's say this is 1. And in the second row, you have 0, 1, according to the rule. And then in the in the third row, you are going to have 0, 1. Hold on, let me sneeze. Let me mute. Excuse me. So, yeah, 0, 1, and 1, 0. Yep. And then fourth row, 0, 1, and 1, 0, 1, 0, 0, 1. And in the fifth row, 0, 1, 1, 0, 1, 0, 0, 1. I lost where I was at. Okay. 1, 0, 1, and then 1, 0, 0, 1, 0, 1, 1, 0. And then 6, 0, 1. And then at this point, I kind of know the rule. So But let me just finish it first, okay? 1 0 1 0 1 0 0 1 1 0 1 0 1 0 1 1 0 1 0 0 1 0 1 1 0 0 1 1 0 1 0 0 1. So at this point you might realize that if you, okay, let's say the third row, and if you divide this string in the middle, the first half is identical to the one before. And if you keep looking at it, yeah, if you keep looking at it, you will realize that the second half is a flipped over version of the former half, as you can see here. So if, okay, so if the first half is 0, then it's flipped over to 1, and that goes the same from here up until the end. Okay, so that is the realization that that you could possibly be that you could possibly take from there. And one solution, okay, I'm going to give you one solution that I did my homework. So okay, so you're going to be given with n and k, and you want to return nth row of the table, and okay, so you want to see first nth row, and let's say in this case it was 6. You are given with 6, and then you're given with k as in let's say 3. 3 is here, and you want to know what this number at this position. Right now we have this concrete example, and you know it will be 1, but you don't know just by this simple given inputs. Okay, so in order to know this number here at this position, because this value at this point is equivalent to the value of the same position in the former row, in the row before. But it depends. It could be flipped over, because if, okay, you're given with a k as let's say 16 or whatever it is, that is later, that is in the second half, then because it's flipped over, the value of the position will be how do you say, opposite value. It's bitwise, so it's either 0 or 1, so it's an opposite value of the same position in the last row. So for example, okay, so I'm not sure how long this string is, but let's say this position. Okay, so this position, all right, so you're given this position, and you want to know how it looks like actually, and this value is a flipped over version of the value at the same position in the last row. So let me say, okay, so this is the position that we want to know, but this is 3. If you consider this is the beginning, because it's split in half, and the latter half starts from here. It's 1 2 3, so it's index 3. So you're going to look at the index 3 of the last row. Okay, so index 3 in the last row is 1, but it's flipped over, so you will deem it as 0. Okay, and it's a recursive operation because, all right, you might know that the same position will give you some sort of insight of what the current row at the same position will look like, but that doesn't mean you know the value in the last row, right? Fifth row, we don't know that either, but we can do the same operation until we get to this point, because we know we start from 0. Okay, so let me do it. Let me do let me go through all the logic. So okay, let's assume this is what we want to know. This value is what we want to know. We go to the 5th row, and this position at 5th row is same as this position in the 4th row, and this position likewise, just likewise, this goes here, and this is same as a flip over version of here in the first row, because it's in the second half. And this position's value is same as here, so it's 0, but notice that we're going to have to flip it over, so it's going to be 1 rather than 0, and that'll give you the initial point, initial data point that we wanted to know its value as 1. Okay, so that is one solution. And let me leave a quick note that I had done a quick homework last night, so I kind of know a rough pathway to solution. So let me just write it. Since I did some homework about this solution, I know the basic idea on how to solve this question. However, I will go through a normal step that I always take. Which is also good for me to revise my understanding. Okay, it's perfect. I'm kind of thirsty. Let me grab something. Let me pause a little bit. All right, let's go. I grabbed some water. Okay, so let me write down. Oh, where am I? My pointer. Okay, there you go. So let me write down what I have just said right there. Key takeaway. First, at the nth row, first flip of first part of the half, I mean first half, yeah, first half is just enough to say it. First half is identical to the one before, to the previous, identical to the previous row. Okay. Second, at the nth row, second half is identical to the flipped over version of the previous row. I'm wondering how to say flip over in more precise way. So it's like bit is let me search bit hunting. Bit inversion, bit flipping. Actually, flipping is a correct term. Okay, sure. So flipped over is not necessary in this case. So flipped version of the previous one. Okay, that sounds great. So using this to trait, we can employ recursive approach to get the value that we want. And let me give you another example of let me give you another example towards explaining second approach. So we can do it. The first approach was more of top-down approach. You start from the exact value that you want it, but we can go a bottom-up approach, meaning you can start from the first row, and eventually you are going to reach to the point that you want to get the value. You want to return the value from the as a solution. And in order to do that, let me remember. So like brute force approach, I'm thinking of something else. So brute force approach is that you're simply going to generate all these array starting from 0. So you pass in this, you pass in 0, and then that'll see the given input, and because it's passed, 0 is passed, and 0 corresponds to 0, 1 in the next row. So 0, 1 is generated, and 0, 1 is then passed in to the function itself, and that will interpret 0, 1, and 0 is interpreted to 0, 1 in the next loop, and 1 will be 1, 0 in the next row, and put them together, and then pass in that combined value into the function itself again, and then it goes again and again and again until it goes to the row value that we want to stop, and then generate again accordingly, and refer to the index that's designated by k. So this is first approach. And by the way, complexity will be O of n. Computational. Okay. And second approach. Generate the next row from the current state until it reaches to n. Return the value that is designated by k. Computational complexity equals to because what you'll be doing is what you will be doing increases by 2 times. So O of 2 times. So n 2 power 2 to the power of n. Okay, and that is arguably extremely slow when n becomes when n becomes bigger and bigger. And here, let me take a quick break. I will be right back, and for a fact I will be pausing this recording so you will notice no difference. Ciao ciao. Alright, I'm back, and recording is back too. Great. So that's second approach, and I think there was third approach. can't come up with the third approach, so let me just refer to people's solution, and this solution's number 779. 779. All right, there you go. And let me just take a look at this solution. Also, I want to open up this here. Okay. Binary tree. Okay. Deem this as a binary tree. Okay, I got a great queue here. If it's a binary tree, yeah. So start from the root being 0, and then you have children that's 0 and 1. That's 0 and 1. And next, how do I put it? Not sure what hit means. Binary tree. Binary tree. Are you sure? Okay, looking at this, parent n minus 1, yeah, of course, n minus 1, and k plus 1 divided by 2. 2. Okay, so, okay, 0 has children 0 and 1, and 0 has children 0, 1, and this 1 has children of 1 and 0, and it goes on like that. Okay, that makes sense. So, the parent of nk is n minus 1. And how do I determine its parent? So k, let's say k is 3 here again. And because this is 1 indexed, because this is 1 indexed, okay, it is 3, and this parent, okay, this value, okay, hold on, it's kind of, no, okay, so, okay, this particular value exists to this, no, belongs to this. So to get 1 out of 3, but let me consider this way. Okay, so 1, 0. To get 1 out of 1 or 0, 1 or 2, if I divide 0 by 2, then you get 0, and it's not the way it should be. So k plus 1. So that means 2 and 3 divided by 2. So 2 divided by 2, 1. 3 divided by 3. No, 3 divided by 2, 1. Okay. 3, no, 4 divided by 2, 2. Okay. 5 divided by 2, okay. So k plus 1 divided by 2. And of course, we're just going to discard the quote. I always forget what is I always forget how to say it. Amari. Quotation. Division remainder. Okay, division remainder. And what is the other? Sure. Quote. It sounds like okay, quotient. I always forget these things. Division, dividend, dividend, divisor. What a divisor? Remainder. Oh, okay. Employ recursive until it reaches to n1 and return 0. Computational complexity will be all of n. All of n. This time I want to implement the third approach, as it seems to be a typical solution. The first approach is good, but it seems a bit tricky to come up with, and I feel like it's more easy to come up with the third approach than first approach, and on top of that, you're not as in the interview, I feel like you're not expected to come up with the first approach. Bit tricky to come up with. and I don't think during the interview I will be expected to do the first approach. Alright, so step 1, the pi, and let me copy the initial code. So for third approach, deem the structure as a binary tree. Where did I put my AirPods? Where did I put my AirPods? Because I'm feeling like listening to music while I implement the solution. Alright, I got it. I will be quiet when I implement the code, okay? So just going to enjoy. I'm going to enjoy myself listening to music. And I hope it doesn't catch, the recording doesn't catch that. I think not, because I'm cutting off. Yeah, because I'm cutting, like, I set up the OBS screening app not to catch any sound from MacBook. Alright. Let me okay. What do I listen to? Oh, Supernova. Oh, Supernova is good. Okay, it seems not catching it. It seems not. Hopefully. Alright, there I go. Something about you is dangerous. I go crazy. Alright, let's go. NK. Binary tree. What? It's not. I don't know what's going on. What the hell just happened right there? Reference, and then if I want to quit, okay, okay. Or I can do, hmm. Ah, fuck. I deleted everything. Damn. Anyways. What? Alright, that's it. I'll see you in the next problem, and I'll see you until then. I mean, I'll see you in the next video. Bye bye. Ciao, ciao.